In this section, we discuss semiconductor junctions, which form the basis of semiconductor electronics, light-emitting diodes, and solar cells. Suppose we have a p-type semiconductor, such as boron-doped silicon, and an n-type semiconductor, such as arsenic-doped silicon, connected together with a good metallurgical bond that would allow free charge carriers to go between. Recall that normally a p-type material has free holes but is charge balanced by the ionized dopant atoms, here negatively charged boron atoms, that have localized an electron, creating a free hole. Similarly, on the n-type side, we have ionized arsenic atoms that have donated a free electron. With no net charge separation, there are no electric fields produced. However, we do have a far greater concentration of holes on the left than on the right, where we can sketch the concentration of holes and electrons as a function of position. So by diffusion, the holes should want to move from left to right. Similarly, with more electrons on the right, the electrons should want to diffuse to the left. The dopant ions are fixed on their atomic sites at room temperature, so they can't move. If holes move to the right, they would meet up with lots of electrons and recombine, destroying both the hole and the electron on the other side. Similarly for electrons moving to the left. This leaves very few electrons or holes near the junction in either region. The interface of the p-type region becomes negatively charged due to the boron negatively charged ions with no holes to compensate. And the n-type region becomes slightly positively charged due to the uncompensated arsenic positively charged ions. We call this interface the space charge region because of the uncompensated charges. It is also called a depletion region because the charge-carrying electrons and holes are depleted. The uncompensated charges produce an internal electric field from positive to negative. The electric field would push holes back towards the p-type region and electrons back to the n-type region. This built-in electric field then opposes further diffusion of both electrons and holes. In this way, the electric field will build up until an equilibrium is reached where the drift and diffusion forces balance. When all the holes in the p-type region are depleted, the concentration of excess charge is the acceptor dopant concentration. We can approximate that this persists for a length we will call the depletion width into the p-type region, W sub p. Similarly, the n-type side has a charge density of approximately the donor dopant concentration with depletion width W sub n. Here we sketch the excess charge in the system. On the p-type side with no holes in the depletion region, the negative charge density can build up to the concentration of acceptor dopant atoms times the electron charge. We then show it relatively constant until the depletion width Wp. While on the n-type side, the donor defect concentration determines the maximum charge density, which persists approximately to Wn. Because the entire system was charge balanced to begin with, it should be charge balanced after the free charges diffuse. Here we see 5 negatively charged acceptor defects compensated by 5 donor defects, more spread out because the n-type side was more lightly doped. This gives us a relation for the relative widths of the two regions that depends on the dopant concentration. Thus, we can expect that lightly doped semiconductors have a wider depletion region than heavily doped semiconductors or metals. If we plot the electric field as a function of x, we should get zero field in the neutral p region that begins to become more negative as we enter the space charge region. It is negative because the electric field would push a positive charge to the left. We can use Gauss's law to sketch the field more accurately. Gauss's law states that the electric field emanating from a region should be related to the net charge in the region. In one dimension, this means that the electric field, starting from the left where it must be zero, is the integral of the charge density as we move to the right. Thus, the electric field remains zero until we reach the depletion width because the effect of the positive and negative charges cancel. Once we cross into the depletion region, we have some negative charges pulling a hole to the left rather than the right, starting a net electric field to the left. The electric field becomes more negative as we move to the right because we have more negative charge pulling a positive charge to the left. The negative charges produce a negative electric field up to a maximum field E0 at the junction. At the junction, we have all negative charges pulling a positive charge to the left and positive charges also pushing it to the left. The magnitude of E0 should depend on the total charge of the depletion region according to Gauss's law. If the charge density in the depletion region is constant up to the depletion width, a rectangle shown here, then the electric field increases linearly, making it a triangle. Beyond the junction, the magnitude of the electric field will decrease as we pass some of the positive charges that now push the opposite direction and decrease the net charge in the integral. Once we get to the end of the depletion region, all the charge is again compensated and the electric field is again zero in the neutral region. Thus, the electric field is only felt internally. To sketch the electric potential, we integrate the electric field. We see that it should rise monotonically to a value V0 given by the area enclosed by the two triangles. If the profiles are indeed triangles, V0 is simply 1/2 E0 times the total depletion width W0, which is the sum of the P and N type depletion widths. With a little bit of algebra, one can relate the total depletion width to the acceptor and donor dopant concentrations and the total junction potential V0, or built-in voltage, which we will derive without assuming a triangular profile. The electric potential V means the whole potential energy increases to the right, but the electron potential energy should decrease. This means that the drift force which comes from the electric potential is, for electrons, a drift to the right, down the potential energy slope, which opposes the diffusion current to the left from the high electron concentration to low electron concentration. In band diagrams, we plot the electron energy, not the hole energy. So for holes, we think of them as floating up the electron bands, here to the left as opposed to down a hole potential energy curve, which would give the same answer. Semiconductor junctions lead to band bending similar to what we found for inhomogeneously doped semiconductors. Here we are discussing a junction of the same type of semiconductor with different doping. The p-type semiconductor with excess holes in the valence band is represented by a Fermi level near the valence band edge, while an n-type semiconductor has the Fermi level near the conduction band edge. To lower their energy, defined by the Fermi level difference, the average electrons would move from the n-type to the p-type semiconductor. This can also be described as the chemical potential for electron and hole diffusion, which leads to the depletion region we discussed earlier. The built-in electric potential exactly compensates for this difference by lowering the potential of the n-type side relative to the p-type until the Fermi level, which includes the electric and chemical potential, is flat, meaning that there is no net force to drive an electron or hole to either side. In the bent band diagram, we see all the bands, including the conduction and valence band edges, following the built-in electron potential energy within the space charge layer, here SCL. Away from the junction, the bands of the bulk p-type semiconductor are flat and still have excess holes in the valence band with Fermi level nearby. Similarly, the bulk n-type region is also flat with excess electrons in the conduction band and Fermi level near the conduction band edge, as we would expect for an n-type material. The Fermi level is entirely flat throughout because we have reached a new equilibrium where there is no net flow of electrons or holes. The constant Fermi level also indicates there is no external voltage, neither applied, zero bias, or produced, no EMF. The voltage is entirely internal. We saw that the built-in voltage V0 is established to compensate for the Fermi level difference between the two materials that are in contact. Since the Fermi level of a semiconductor is engineered through its doping, we can relate V0 to the dopant concentration of the semiconductor. Recall that the electron concentration N is related to the difference between the Fermi level and the conduction band edge energy. In the Boltzmann statistics approximation, the relation is an exponential where the effective density of conduction band states is used. Different Fermi levels give different electron concentration, where these other parameters are constant for the same material. Taking the natural logarithm, we see that the difference in Fermi levels for two differently doped materials should be proportional to the log of the ratio of the two electron concentrations. Thus, the built-in electric voltage V0 should be equal to kT over E times this logarithm. The electron concentration of the N-type material should be approximately the donor dopant concentration, which we should know from making the material. For the P-type material, we use an acceptor dopant that provides a hole concentration, which is related to the electron concentration through the mass action law. The NP product should be equal to the square of the intrinsic electron concentration. So we can get N2 also in terms of the prepared acceptor dopant concentration. Finally, this gives us the internal voltage in terms of the dopant concentrations of the two materials and the intrinsic charge carrier concentration, which depends strongly on the temperature and band gap of the semiconductor. Note that this derivation doesn't assume any particular interface structure or charge profile in the space charge region. V0 is simply a property of the bulk semiconductors. Also, because the Fermi level also determines the work function of the semiconductor, the average energy of adding or removing a charge in equilibrium, the built-in potential can also be described as the difference in work function of the two materials.